Points on the perpendicular bisector of a line segment are equidistant from the endpoints of the line segment. So here's a line segment. Here's the perpendicular bisector. This line is perpendicular to the line segment and it cuts it in two, bisects it. So that's what the ticks indicate. We have two line segments formed that have equal lengths. So what this says is that if we take any point on the perpendicular bisector, let's say we take this point here, then the distance of this point to this point here is equal to the distance of it to the other end point. So we want to prove that these two lines have the same length. Let's call the point on the perpendicular bisector x. I could have picked any point on the perpendicular bisector. I could have, say, picked this point here. Doesn't matter. So to prove that a equals b, we note that we have two right angled triangles formed here, because this is the perpendicular bisector, of course. So we can apply Pythagoras to both of these right angled triangles. We can say that the square of the hypotenuse of this right angled triangle, b squared, equals the sum of the squares of the other two sides, i.e. c squared plus f squared. When we look at this right angled triangle here, the square of the hypotenuse is a squared. That's equal to f squared plus d squared. Now, if we look at c squared plus f squared, we know that c is equal to d. That's part of the construction. This line bisects the line segment. That's a given. So we can replace c with d. But d squared plus f squared by Pythagoras is just a squared, as I said earlier. So we end up showing that b squared equals a squared. If we take the square root of both sides, it means that b equals a. So that's one way to prove that the distance of any point on the bisector, which I'm calling x, to the endpoints is the same. So we've shown that these two lengths are the same. Now another way to prove this is to show that these two triangles are congruent. One of the conditions for two triangles to be congruent is that two sides and an angle in between the two sides have to be the same in both triangles. Well, obviously f is the same in both triangles. This is a common side for both triangles. We're given that d is equal to c, so there's another side that's the same in both triangles. And we also have that the angle in between those sides are the same. So the abbreviation for this condition is SAS, which means side angle side. So we have that condition for both of these triangles, which means that the two triangles are congruent. And if the two triangles are congruent, then the sides opposite the equal angles in both triangles are the same. So the side opposite the 90-degree angles are A and B, so A must equal B. Also, we can go a bit further actually. Since we now know that these two triangles are congruent, we know that this angle here is equal to this angle here. Well, we have an isosceles triangle, and that's covered in another video. We've actually proven that these two angles are equal in another video using a different approach. Well, actually it's a very similar approach. It's almost identical to this. So obviously then the remaining angles are the same. So this angle here equals this angle here.